Okay, so this is going to be our office hours video for homework number 1, problem number 5. I never know whether to call these problems or exercises or something else. Questions. Yeah, I heard somewhere some people like hear the word problem and are put off by it because it's not a problem, it's a solution or something. Okay. So the next couple, I'm going to try to record a couple of these today. The next couple are going to be a little less polished, I think, but I need to get these out. And so what I'm going to do is while I'm working on these, I will be kind of walking through a little mentorship on how to search for code and a little less polished on getting direct to the solution and explaining things. So here's problem number 5. And we've done videos to support 1 through 4. And okay, so let's see, screen sharing, just checking things. And I want to make sure we're recording. Pause recording, start recording. Okay, we're recording. Okay, so let's take a look at what this says. The data set CHD data.csv. Okay, so let's start from what that means. There's 2 places, probably a couple of places where you can get to that data set. The pretty sensible place, if you go to files, you go to computer, and in our collab, you'll find chdata.csv. You can find it there. Also, I'm going to add this to our chat, which in the screen recordings, there's a spot where you can access the chat info. So I just put this here in the chat. This is a coronary heart disease, and I built this uploaded data to Kaggle. And Kaggle's a great place. So this is a good place to get used to. It's going to be really helpful in your homework. So here's this data set. Just take a look at what's here. Right, there's a nice downloads plot. April 2023. My guess is maybe that's the last time I used this in this class. Yeah, I have 13,000 views on this one. That's cool. 15,000 downloads. So it's more than just I put it up for this class. But there's really good let's see, data card. There's really good information on data sets in Kaggle. It's a great place to find things. So me as the owner, and I don't know if you ever do classification on this, you can look through what other people have done to find out what works and what doesn't, which is really great for Kaggle. I can't say enough about this. Somebody did some discussion on the alcohol variable. I'd be interested in going and reading that. Can't say enough about just the use of going and look at this. So let's take a look at what's here. The context, the data, this is something I wrote to describe it. The data set CHD data.csv contains cases of coronary heart disease, right? And so a little description of those, that's good. There's usually some summary of the data, right? And so this is systolic blood pressure, tobacco use. So you get some little histograms of what the different column values for the different columns are. Just looking at this, what I see is like tobacco is not a normal, doesn't have a normal distribution. Maybe that's a looks like maybe it's a binomial distribution or something like that. Same for systolic blood pressure, and that makes sense. That's like if you think about a binomial variable being success or failure, for successful failure of does the person smoke or not, or whatever. It makes sense that those would have binomial distributions. There's a nice graphic. The problem was I was trying to find a place where we could see this graphic. I hit open in a new tab and it downloads it. I mean, that's fine, but okay. So, right, kind of describes, I put this together just to describe the different impacts and what the variables mean. Okay, so that's where you can get that data, and I'm gonna look at the code, and here's a number of homeworks that people have put together, and you're free to, anything that's on Kaggle or on the web, you're free to go look it up. And if somebody has homework 3, you know, I'm okay if you go look up somebody else's work and you find somebody else's work on the same problem. Okay, as long as you take it and you read it and understand it and then write your own. And I'm going to make this rule. I mean, I don't have any way to check it, but if you find somebody else's work and you're going to use it, do 2 things. Don't copy paste from their work into yours. Feel free to like type it in exactly right off theirs, but I want you to go through the typing. That's for your benefit. And also for the sake of just like ethical care, like to have good ethics, document that you used it. And that's, you don't lose any points. And when I see that, I'm going to be like, okay, that's a good ethical person and they're doing their work to go find somewhere where they can rely on. Also, no guarantees when you use somebody else's. Right. So, okay, so let's CHD data preparation, notebook copied with edits by me. So I'm guessing this is related to our homework assignment. So let's copy and edit. Okay, so let's get going with this. Let me bring back the homework. And this is part of where I say today, I need to get a bunch of the homeworks out. Homework, like these homework videos out. So I have a little more chatting. I usually try to be quick and concise, but I just want to make sure I get them all out. And the quickest way to get it out is to be a little chatty and describe things. So, okay, so we have systolic blood pressure. So let's go through, let's see this and see where it's opened up. So we're going to import NumPy and Pandas. You should be used to importing those. This reads the CSD data and sets it up. So let's execute this. And then that. Okay. So one of the really nice things about working in Kaggle is you'll get the same environment, like Python environment that I'm working in. So you will, when I created this, there's idiosyncrasies in Python and updates and things that become not backward compatible. So, but the Kaggle saves the environment along with this notebook. So even if there's updates that would make this code no longer, work or require some modifications in a new version of the code, it'll work right in here. Okay, so systolic blood pressure, that's SBP. Yearly tobacco use in kilograms. Okay, so this is interesting. And it's maybe it's not super important, but for taking ownership and understanding. So this is how many kilograms the person used. 3.6 kilograms is the average amount of tobacco. I have no idea if that's a lot or a little. I never smoked a cigarette. I've never smoked a cigarette. So I have no idea. Low density lipoprotein, LDL. So there's, if you're a doctor, that probably makes a lot of sense to you. Adiposity makes me think of the Doctor Who episode with adipose. I think it was adipose. Family history, which is a 0 or 1. Now, this is interesting. Let's see, where's family history? Alcohol, age, adiposity, type A. Oh, it's not listed here because in this describe, this is an interesting thing. The kind of thing that we can talk about a little bit when I'm taking my time on these. Describe doesn't give you all of the values. So if you look here, this family history column is present here when we just type in CHD data, But when we say, here's our data frame, these do describe, it gives you these summary statistics for each. Family history is a categorical variable, which is like a true, false, present, not present. So it's not going to give you this information in the describe. Type A personality score. I'm guessing they had people take a personality test, and there's part of the output is like, how type A are you? Obesity, which is in body mass index. So this obesity is a BMI, and the mean is 26. Right, and you can see the max is 48. It's interesting going through these and seeing, okay, this obesity variable, what does that really mean? It's a body mass index. Alcohol usage. So here's a column for alcohol use. And I wonder what the variable is. Maybe it's, what's the mean? The mean is 17. So drinks per month, I don't know. Hi, Tyler. Good morning. Age, pretty self-explanatory, and then the diagnosis of coronary heart disease, which is yes or no, 0 or 1, coronary heart disease. So, okay, so Tyler says he can only use the chat at the moment. Hey, that's no problem. I'm recording the videos. I'm going to walk through how to do some of the homework exercises and provide some code. And so this is for Tyler or for anybody who joins during these. Feel free to join, feel free to hang out, feel free to ask questions. For the most part, I'm just going to be doing the presentation on the thing, but if something comes up that's interesting, feel free to chime in, or feel free to come and go and, you know, watch on the recording. That's fine too. Okay, so so far we've just kind of walked through this first paragraph, which is what the data is. And let's talk about reading this, because part of the challenge of these homework assignments is understanding these. And I have a scheduled, so John Kropko or Professor Kropko, Dr. Kropko, he's helping us go through, helping us being the teachers, and rebuild a lot of the course material. This Bayesian machine learning course, I am super passionate about. It's so important. It's so good. There's so much meat. Unfortunately, the course material doesn't work great in the online environment. So it's really valuable. But I mean, the problem is it's so sort of current and latest, and there's no single good textbook for it. So how do you design a course when there's no single textbook that really gets the things at the level they should be at, right? If your deep learning course, you had a fantastic textbook and there's a lot of good material. For your machine learning course, the Turbashani book is excellent. You have that in PDF. There's a lot of resources for it. That just doesn't exist for Bayesian machine learning, right? So I'm working on getting a textbook, writing a textbook. Professor Brown and I are. So a lot of these videos, I don't know if you learned in the lesson videos, they don't sync great with the material and probably your background understanding. I know a lot of students, like, just depends on how much math you've had, and really not just math, but math specific to systems engineering and probability and statistics and operations research, I think too. Those might make sense or might not make as much sense. So that's okay. My goal is to make that transition between, you know, the latest research stuff and how to use them and how to make sense of them, and helping you all learn how to do that. Okay, so, and the one problem is that it's my job to make the transition. It's impossible to make that transition and have everything in the course be timed, be well timed, and be clear up front, because the videos don't match. We don't have great material for the readings, but we have updates planned for all that. Of course, it doesn't help you. So just, I don't know. Sorry to ramble, a little bit inside baseball, as you say. Okay, so what does this mean? Perform Bayesian analysis of these data. So this means we're going to use, when somebody says do Bayesian analysis, it means we're going to do priors and probabilities, and we're going to get some probability distribution on the parameters. And I can't emphasize this enough, that often when you see probability distributions in the parameters, or we call that a posterior probability distribution, often those parameters are things that we think of as being fixed. Like, what's the probability of getting a heads on a coin, right? I worked a lot on that specific example. What's the probability of getting a heads on a coin, to emphasize that the parameter is P there, but it's really an unknown. We pick up a coin, we don't know whether it's fair or not. And I'm pretty sure it's fair, but I don't know if it's fair, if it's like going to have heads like 0.5000001% of the time. Like if I picked up a coin and flipped it a billion times, is it slightly biased either to heads or tails? I would think it probably is biased one way or another, just weight and how things tumble. But I don't know. But so that P, we think of that as fixed. We think of it as 0.5, but really we don't know what it is. And that's the whole idea in Bayesian methods is we try to understand those parameters. So we talk about getting a probability for something. We really mean when we talk about a posterior probability for something, we really mean a probability distribution for that thing. Like think about all the possible values that thing could take on, right? For a coin, the thing is P, and it could take on any value from 0 to 1. And we want a probability distribution that gives you probability for any of those values. Then it comes into whether it's continuous or discrete, right? If we think of 100 values, just estimate round everything to 2 decimal places like 0.53 or whatever, then it's a discrete distribution. It's what's the probability of each of those individual values. If it's continuous, which would make more sense for a coin, right? Like it could be 0.5000001, right? It could take any value. We need to do what we do with a normal distribution, where it's not a probability for each value, it's a probability density function. And when we estimate probabilities, we would say, what's the probability it's between 0.5 and 0.51, or we have to give a range. Okay, so that's what Bayesian analysis means. We're going to look to find a probability distribution for parameters. Okay, so we got to find out what the parameters are. So it finds the, posterior. So this tells us we're going to find a probability distribution on something, on a parameter. And then it's marginal. Now, marginal means, remember when we had, let's see. Got a wait word for base ML. Homework 1. So let's take a reminder of what marginal probability distribution means. I'd be curious if anybody has opinions. Do you like the light background or not? So if we think of having two variables, X and Y, and X can take on either A or B, and Y can take on 0, 1, 2, 3, 4. And right, we have this whole table. So we're going through what marginal distribution means. We have a probability for each of these. So probability of getting an A and a 0 is, now I might mess this up. Like all these things that I write here should add up to 1. 0.2, so what I have, 0.56. I'm just going to put a bunch of zeros in. It's going to be a little bit boring. 0.1, 0.1, and 0.1. Okay, so suppose everything here adds up to 0. If it doesn't, let's make it add up to 1. Okay, so the marginal distribution for X means we have a probability for A, and we get that by summing across the horizontal row. So we add up all those probabilities, and we would get 0.1 plus 0.1 plus 0.3, that's 0.5, 0.6, 0.6. The marginal distribution for B, we sum these up, and we get 0.4. So our joint distribution is P of A comma B, that's shown by this table. The marginal distribution would be, sorry, it's X. It should be X and Y. The marginal distribution is a probability distribution. We might write it as P of X. And we write P of X, we mean the probability distribution for X. So that would be the probability distribution that has P of A equals 0.6 and P of B equals 0.4. Now, sometimes just notation wise, we write P of X sometimes when you see that, unless you know the context, you're like, what is that? That notation doesn't describe enough to me. And this is just notation that's standard with probabilities. I don't know, slightly bugs me, but I don't have a better answer. This P, we think of it as being a function and you put something into it. But this notation, this is like a generic way to write the function. This is where we're taking a thing, X, a possible output, and we're putting it into P, which maybe you think of it as a function or something. It takes subsets of your state space as inputs and outputs for variables. So think of this as like, we often write f of x, and think of this as like f of 2 and f of 3, right? Where f is like your standard function in like pre-calculus or whatever. So this is a way of just writing generically, this is the function, and we put x as the input, and then here these are specific values. So, but anyway, the main takeaway here is that the marginal distribution is what you get when you take all the values of the distribution and we sum out the contribution of y, or we sum across the rows and we get this, and called marginal distribution because we write it over on the side in the margin, right? And so just to kind of complete this picture, this is the sum over all values of y of p of a, or we should say all values of b, or maybe b in the state space of y, and it's the probability of a comma let me get a better way to write it. I'm going to write it the kind of the clean way. It's the probability of getting an a from x alone, and we might write this as probability that x equals a. That's the sum over all I, and I'm going to use I because these values that are inputs for y are integers, and so I might stand for an integer, or maybe n, right? So n stands for one of the values. It could be a value for the variable y. So the probability of a comma n. And to just be a little more clear, that's probability of a comma 1 plus the probability of a comma 2 plus probability of a comma 4, right? That's what we get. This here means we just summed across this row, right? And we could do marginal probabilities in the other direction. We could say probability of y equals 0. To do that, we just sum down this column, and that's 0.3. Okay, so when you see marginal probability, think of this picture. Think of summing. You fix one of your variables, and you have two variables in your distribution. You fix one of them, and you sum across all possible values of the other. And it could be a sum. It could be an integral. It could be you could be fixing more than one variable by itself. You could fix 2 or 3 and sum with respect to 2 or 3 other ones, right? Okay, so probability distributions for the means. Okay, so at this point, we see the means here. We say we have a means for these two groups, and we want to get a probability distribution for what these means are, right? So what we're thinking here is each of these groups has a probability distribution describing these values, right? Whether there's tobacco or not, or what their type A personality score is, and all these different things. And so we have a mean value. We could take these two groups and we can just compute the mean value and look at what the mean value would be for these groups. But we don't want to know, hey, just what the mean value is. We want to do this in a Bayesian way. And we want to say, how sure are we what these mean values are? Or what's the probability distribution on the estimate of each of these means? right? Just like we pick up a coin, we don't know exactly what the p-value is for the coin, right? Probability of heads. Here we have a mean for each of these groups, people with coronary heart disease, not coronary heart disease. Okay, so so we need to separate out this data frame and make two different groups, one with coronary heart disease and one without. I'm going to pause the recording for just a moment, take a phone call, say hi to my wife. She's visiting friends, and I got to get a new Monster energy drink because I need to keep going. Okay, pause, which of course for me, it'll be a pause and I'll come right back. But if you're watching the recording, I'm just going to like blip or something. Okay, so let's see. Apologize, I got to reorient myself. So we're looking at the probability distribution for the means. And so in our data, we're going to have the means for these two classes, with coronary heart disease and without. And so there's a little bit of information before we go calculate this means. It says you should first standard scale. And so that means subtract the mean from each variable and divide by the standard deviation. So let's go ahead and do that. And it says do that to all the numeric variables and remove the family history and don't scale coronary heart disease. Apologize for any drinking sounds. And definitely, if anybody has any way to get Monster Energy drink to send me a little promotional payment, I'll appreciate that very much. Okay, coronary heart disease. So, okay, so let's run through these. We ran the rows above. Here's the code. So coronary heart disease is a data frame that we loaded in. And so when you want to drop a data frame in columns, you just do dot drop. Now, if you were like, I don't know how to drop a column from a data frame, so how am I supposed to know that? You could always go pandas data frame. How do I drop a column? And there's a good chance whatever comes up in the top is going to help you. I really like W3 schools and Geeks for Geeks. Geeks for Geeks tends to give you a very concise answer, right? They set up the data frame in their example. They give a really nice example. So I go through here a lot and to say, how do you drop it? And it, there's examples and there's a little more detail of just like one example, right? It tells you something about how to call the axis. You could also use ChatGPT and type in, how do I drop a column? Okay, so after I drop that, I do coronary heart disease, CHD data, like I did here, and you'll notice up the first time I did it, it had the family history. Now in this time, there's no family history. A little warning when you're doing Jupyter notebooks, we have the same variable here as we did above. Or we didn't change the name of CHD data. Sometimes, the disadvantage is if I rerun this block, I'm now going to get a different answer. Like it won't have that family history. So if we watch, boop, so the variable's now changed its value, right? So that can sometimes cause confusion. Sometimes you want to call this CHD data without family history or something, but it doesn't for this, doesn't matter. Okay, so here's our dot keys, gives us the column headers, right? And so it's a data frame which you can treat as like a dictionary, and the keys are the headers. And this says give me the keys 0 through 8. So if I didn't do the 0 through 8, and this is always kind of a good practice when you're looking at code, modify it a little bit, see what happens, make a guess on what you expect. Now it includes this CHD column, but I only want the first 8, right? And the reason is these are the ones we're going to normalize. And so let's look at just the tobacco column. So average. So each row is an observation or person. And what's given is the number of kilograms per year that person uses in tobacco. Okay, so this is a nice block of code to do the standardizing, right? So we have a for loop. We're going to loop over the keys. In Python, you generally don't loop over an index. You want to loop over something like, in this case, the key, some iterable. It doesn't matter if you're used to coding in like MATLAB or something where you iterate over indices. I could iterate over that, but each time it goes through, this key is going to take on a different value. It's going to take on the next value from this list up here in this index. Okay, so each time it goes through, it's going to print standardizing, and then this text, and then plus and key is a string. So it's just going to add that in and tell us standardizing. And then it's going to take, this says pull the column, right? You put the key in there and you get this column, and it's equal to itself minus NP mean of itself. So it subtracts off the mean of itself. Then we take the column and we set it equal to itself divided by the standard deviation of the column. And so let's go ahead and do that. And it's really quick. And I like the fact that it tells us this so we can know for sure that it worked, or that it was at least running. And then we can check that it worked. And remember this describe, if we go up, when we did describe originally, it gave us all the numeric columns, and it gave us the count, how many values, the mean and standard deviation. So you mean is for SDP, let's look at that, was about 138. Mean for tobacco was 3.6. Look at the standard deviations. Now that we've normalized or standardized, what was the word in the notebook? It says standard scale. So now that we've done our standard scaling, we have this, and we should have a mean of 0. And these means, except for the CHD one, these means are all very close to 0. And a standard deviation of 1. And you can see we have a standard deviation very close to 1. So it worked. Okay, so what we want to do now is separate out the two classes. There's a class of people with coronary heart disease and people without. And we're looking at the means of each of those classes. So we look at CHD equals 1. And so this gives us the information of whether each observation or each person either has coronary heart disease or does not have coronary heart disease. Now we're going to make 2 data frames. We're going to take a data frame and we're going to input into this data frame this, which is going to give us, let's go ahead and take a look at what that would give us on its own. And one nice thing about Jupyter Notebooks, if you're ever not really sure what something does, you can always make a new block and run it just like I did. And so this gives me true or false. In fact, it's what we just did above, I guess, for each of these, whether they have coronary heart disease or not. So this is going to be the indexes. It's going to be true for everyone with coronary heart disease. And it's going to say, take the coronary heart disease data and give me a new data frame, but just pull the rows where this is true. It says, give me data frame, pull the rows where it's false. And so that's going to give me 2 new data frames. We didn't output anything. So now we're going to check that it worked. So here's the coronary heart disease positive and coronary heart disease negative. And we look at these, and the first thing I notice, coronary heart disease, they're all 1s. It should, sometimes it tells you the length of the data frame. And okay, yeah, so if you don't do the describe part, you just say coronary heart disease positive. It says 160 rows. So there's 160 rows, or 160 observations, or 160 people in that data set. And it says coronary heart disease, the count is 160. Oh, okay, so the count down here is 302, so 302 coronary heart disease negative people. I was expecting it to give me the sum for that column, but it doesn't. Okay, so here's the important thing. The mean for the coronary heart disease negative group for the coronary disease column is 0, right? They all have 0 coronary disease. That's kind of what we hope. This is just confirming that this worked. The mean is going to be a 1. So we can look at these values. Let's kind of just sense check. Blood pressure is 0.26 for average people with coronary disease. And on average, systolic blood pressure was negative 0.14. And remember, this is the standardized blood pressure. So people with coronary disease have an average systolic blood pressure of 0.26 standard deviations above the mean, and the mean being out of the whole group. People without have a value of 0.14. And so maybe SBP. I'm going to try something here. Okay, so that's this column. And I want to take a little bit more view into doing a little visualization of what we're working on. So write code to plot a histogram with KDE of the values from a single column of a pandas data frame. Right, so this is both, giving us kind of a nice little bit of practice using ChatGPT, and should give us what we're looking for. So CHD positive is our data frame, so we need to go through and replace everywhere we have that. The column name is SDP, and so let's see if that works. And probably need to import. I always like to put my imports at the very top. Probably don't need to import pandas a second time. So just make sure I'm recording. I got my screen share. Every once in a while, I'll go back in a video and realize that I've forgotten to import a big piece of it. Okay, so import all those pieces since I'm going to use them down below. And Seaborn has no attribute hist plot. So what does that mean? So I'm guessing Seaborns are often imported as SNFs. Hist plot gives you a histogram plot. Let's see if we can ask ChatGPT to fix that error. Now I'm guessing the version of Seaborn that so I asked it to fix that. I apologize for the confusion. Starting Seaborn with runners, his plot function has been replaced with hist plot. Wait. Did it just say the same thing was replaced with itself? Okay, let's go see. My guess is that, the advantage. Okay, this is ChatGPT hallucinating, which is kind of funny, right? It thinks this thing's been replaced by itself in this version, which is wrong. So it might be just hist. SNS dot. Sometimes autocomplete will give you Seaborn hist. So maybe it's hist plot, not hist plot. So, one of the really important things in learning to code, especially in like the machine learning world, is learning things like this. Like, how do I deal with things that don't work, right? How do you debug? And I remember the first time working with somebody who was more skilled than I was, and I realized, oh, they just do a Google search, right? Okay, so here's what I want to do. And this is really the main reason I'm doing this. CS negative is really, this is going to give us a one-dimensional version of what this problem's asking us about. Column to plot positive. I'm going to extract these two, the positive and the negative ones, and I'm going to plot both of them on this screen. So blue is going to be positive. Let's make the negative one red, and is it label? It's either label or name, and I always forget. CHD positive. And CHD negative. And PLT dot legend. So that'll add a legend. Okay, so this is really interesting. So this is the CHD positive and CHD negative. And when you look at these two plots, you might think, let's go back here. If you look at the two means of these, so the mean for the CHD negative people is negative 0.14 standard deviations. And the mean for the positive is 0.26 standard deviation. You might think, oh, there's like a quarter of a standard deviation separation between those two. Is that meaningful, or is that not meaningful, right? And we come down here and we see, well, the blue, the positive ones, people with coronary heart disease, there's a little bit of a shift to the right, and the negative ones, there's a little bit of shift to the left. So if my SDP, my systolic blood pressure is on the lower side, then I'm less likely to have coronary heart disease, and that makes sense. But just looking at the separation between these two, it's not a giant predictor. It's not like, oh, if it's high, I have to be in one category. If it's low, I have to be in the other category, right? So that's the kind of thing that we're really getting at here, is how separate are these means? How meaningful is this difference? And if I was going to make a medical decision on them, right, how much can I base that medical decision? Should I, if there's a procedure that will help a person if they're in one category or another, but a procedure costs $10,000 and might cost the person to lose a finger, right? Those are two bad outcomes. Like, I need to know the probabilities of different outcomes, just like we're helping Uncle Iro pick his flower or tea, to know, really what decision I should make. One of the things we can add to these plots to help customize things a little bit is to indicate the number of bins. I always forget whether it's bins or n bins. I guessed right. Okay, so bins is how many bins we use in our histogram. And so we see here that you get a little bit of a finer grain picture, right? A little less coarse. And we see that there's plenty of coronary positive people in the blue that are distributed, all the way from -2 standard deviations all the way out to 4. Coronary negative, not many out to the 4, but 2 standard deviations above, all the way to 2 standard deviations below. So and give you a sense of that spread and how meaningful it is. So what we want to do is we want to do analysis rigorously, getting probabilities. That's similar to what this sort of just looking at the values analysis is here. Okay, so here's a standard textbook question for the data, which I'm looking at the notebook, and I copied and pasted the question from our class question. Perform a Bayesian analysis of this data that finds the posterior marginal probability distributions for the means of the data of patients with and without coronary heart disease. So we've kind of just followed along computing these means, and we've done that standardizing thing, but we haven't talked about really the marginal part, and we'll see where that comes in. And what we're doing is we're looking at the well, okay, let's read on. Your priors for both groups should assume means of 0 for all variables and a correlation of 0 between all variables. So I copied this from the assignment. I assumed somebody already, because I already have the standard scaling above, that the standard scaling's been done. And actually now I kind of like this piece here that gives me this, and maybe I'll clean it up in 50. I'm going to add this and save it as part of the notebook, because I kind of like this little piece, right? It shows. Let's examine the difference between the distribution for the systolic blood pressure distributions for the CHD positive group and the CHD negative group. Right, so that's what we're doing here. Right, so this is like just looking at the one variable for the two different groups. Also, this isn't Bayesian. This is more just looking at the distributions. This is what our likelihood would be, right? This is the, you could think about this as probability of, it's the PDF for SDP given CHD positive and I'm writing latex in here. I don't know if that's gonna. Negative. So really, we're looking at these two probability density functions. See if that worked. No, that didn't work at all. So how do I put latex in a markdown box in a Jupyter notebook? Okay, so maybe I need to do begin equation. So this little bracket is latex for begin equation, but maybe I really need to do it with those, which are kind of the full latex notation. I really don't need to do it in latex. That's fair enough. I want the probability density function for SDP given the coronary hair positive. So that's really what these two are, the PDFs for the parameter value given these two categories. Okay. So sorry for the little excursion there. So let's check the mean of each class to get a first look at the separation. So we're going to look at the mean for each of these classes. So this is going to compute the mean for each classes, which is just this top row right here. So this is the mean for coronary heart disease positive. This is the mean for coronary heart disease negative. Now let's kind of look at these one at a time. So SDP, blood pressure, we see a separation, and it's modest, but I would still say meaningful, both with comparing those values and looking at the plots above, right? There's a little separation here. It's a meaningful separation. Out here, the blue is higher than the red, meaning positive is more likely than negative out here. On the left-hand side, it's red is more likely than blue if you're over there. Meaning you're more likely to be in the blue class if you have high blood pressure. You're more likely to be in the red class if you have low blood pressure, but it's not a distinguishing factor. Okay, let's look at the next one, and the next one is tobacco use for a coronary heart disease person, about on average 4.11 kilograms per year. Coronary heart disease is negative 0.21. Again, that's a nice bit of separation, right? We saw this like 0.35 difference, 0.35 standard deviations difference was meaningful here. This is a little bigger separation, so that's probably, meaningful, but not conclusive. Similar here, this is LDL cholesterol. So higher cholesterol for people with coronary heart disease. The next factor is adiposity, what does adiposity mean? Just means adiposity, okay? This seems to be less of a separation, 0.14 to 0.075. Let's go see what that category is. That's the one after adiposity. That's alcohol. So the alcohol separation doesn't seem to be very significant. And so this is what we're doing now, is like feature importance, or how impactful each of these different variables are. But we're using kind of a Bayesian thinking instead of like putting it into a random forest and saying, tell me feature importance. And we really haven't gotten to the Bayesian part because we haven't incorporated priors and turned these into probabilities. We're just kind of looking at the difference in the likelihood functions. 0.3 to 0.07, that's not very significant. That's age. 1, 2, 3, 4, 5, 6. So this is the sixth one. 1, 2, 3, 4, 5, 6. Okay, so maybe it's easier to compare them on here where I've got the labels. So 0.1, let's go type A, 0.14 to negative 0.05. That's, I don't know. It's still the difference. It's not giant. Let's not overthink these. 0.17 to 0.07 to negative 0.07. The difference is not giant. Let's think of like in a baseline, this is a 0.35 standard deviations difference for SDP. And we saw here from this plot that seems to be meaningful, but not, conclusive. So 0.35 is okay. Obesity, a little bit of a difference. Alcohol 0.008 to negative 0.045. So that's the first one that if you look at these means, that the mean for the SDP column is less than 0.1. So the alcohol separation is the smallest, just looking at these. Oh, and age is a big deal, 0.5 standard deviations above and 0.25 below. So the separation there is 0.75 standard deviations. Okay. So what we've done here is we're converting these to data frames. They were converting the data frame data to NumPy arrays. So CHV positive. Oh, okay. We've been doing two steps here. And so this is getting a little bit ahead. So here we're just looking at the means, but really what we did above, and maybe this would be kind of fun. Let's do something fun. Let's have fun. Where do we iterate through the keys? Here's where we iterated through the keys. And so what I'm going to do is do all this analysis, but for each variable, right? We just looked at systolic blood pressure. And let's make the title histogram of the PDF, because it's really, we're going to think about it as a likelihood function with kernel density estimation for this variable. And when we say likelihood, we mean the likelihood say for each class, meaning each class meaning a positive CHD positive and a CHD negative class. So we're gonna take this code, which was pretty nice, and we're gonna turn it into something that is gonna do the same thing for each of our variables, right? And this is kind of cool. So I'll leave you to like look at those and think them through. The one that interests me is the alcohol, right? The interesting thing is these are just taking each variable by itself, right? This one, obesity, that's a kind of a cool separation because it's the same shape and it's easy to understand. Ooh, what was this for age? Remember we saw age was a big distinction, and that's really interesting. Where was alcohol? Alcohol use. So here's the alcohol use. So I don't know. That's interesting. As you use more alcohol, what's the impact? It's a little hard to tell on the scale. I don't know. Now, I know I'm probably maybe taking too much time on this, but I don't know. I like these with a little bit of a grid on them. You can actually add a grid on like a finer one with fainter lines as well, which I like. I like that appearance, but I usually like to put a grid on plots and graphs. So, okay, so that's really nice visualization. By the way, if you're doing this for a project, thinking about your project for the end of the year and you were working on this, this is the kind of thing that you really need to do a good job with the project, and then talk about these the way I did as part of your presentation. Okay. Oh, and by the way, here's another thing. When I look at these aren't really normal distributions, right? None of these plots, let's look at them. Obesity, that looks like two normal distributions. Maybe these are two normal distributions. Certainly not, I don't know, LDL. That doesn't screen normal. I don't know. That's always a thing to think about. The tobacco certainly doesn't. That screens not a normal distribution, right? And maybe that's why when we do a normal distribution type analysis, we see there's not enough separation. or it's not being used. So we're assuming everything's normal, right? It's an implicit assumption when somebody says take them to standardize by subtracting the mean divided by the standard deviation. They're implying you're assuming things are normal. And now we're using a multivariate normal distribution to model the classes. That's implicit by computing this covariance matrix. But looking at those, it's reasonable to work with a bunch of them as normal distributions. But certainly not tobacco. Okay. That's the kind of thing that matters when you're doing like real analysis and not just a homework problem. Okay, so perform a Bayesian analysis of these data that finds the posterior marginal probability distributions for each of the means for the data of patients with and without CHD. You should first standard scale. We did that. Separate the two classes. We did that. Okay. Now, here's where here's where it starts becoming Bayesian. Your priors for both groups should assume a mean of 0 for all variables and a correlation of 0 between variables. There's going to be some standard ways to work with this. And you should assume all variances are equal to 1. So let's kind of take a look at the code, and offhand, I like up to here, I remember clearly everything we're doing. Here's CHV positive. So to do this, we're assuming there's these two groups. Let's back up and get big picture. We're assuming CHD positive, CHD negative. There's, what do we have, like 8, I forget if it's 8 or 9 dimensions. 1, 2, 3, 4, 5, 6, 7. So we have 8 dimensions, so 8 variables. So if these two means of these two classes in 8-dimensional space. So you picture, you're in 8 dimensions, you have these pieces that are separate, and then there's a spread around each of these. We're modeling that spread around each of them with a multivariate normal distribution. And so we're going to compute the covariance for each of those. So here's the covariance matrix. Sometimes it's useful to look at this as an image covariance matrix. And so you'll always see kind of high values down the diagonal, and this gives you a sense of the correlation between variables. So variable 3 has a fair amount of correlation with variable 2, because it's a little brighter there. The places where it's darker, you get anti-correlation. So I don't know. It's not worth thinking about that too much, but I just kind of want to mention that that's sometimes a useful thing to do, is to look at your covariance matrix as an image. Okay. And these are in the covariance matrix, these are the covariance values. This is the covariance, I call it the correlation. It's covariance between, this would be variable 1 and variable 2, right? It's covariance between variable 1 and variable 3. Okay, so we're going to take this CHD positive data, drop the coronary heart disease column, turn it into a NumPy variable, and look at that. So this is our data from the coronary heart disease, removing the coronary heart disease column and just looking at the CHD positive side. And then we're going to take that data and compute its covariance using numpy.cov. And my battery's running low. I'm going to go pause the recording, plug my. Okay, so I realized we've been going through the coding part, and we've hit a spot where the coding part starts getting into how do we answer this question. And so we need to take a little step back from the coding. I was walking through the code that was here that I was looking at. And so the question asks us for the posterior marginal probability distributions for the means. Now, a lot of times people make assumptions, and it's fine to get used to this in the field. This is a standard question from a textbook, but it's implied that the assumption you're assuming multivariate Gaussian distribution for these means, right? If we look up here, right, we're saying how separated are these two means. These are just the likelihoods for the separation between the two probability distributions or the means for those. But we're assuming that we have these two means, that there's a multivariate Gaussian distribution that describes the separation. And that's a fairly strong assumption. And we saw above that maybe it's useful, maybe not. But when you have 8 dimensions, it's usually important to make an assumption like that to work with things. So let's work on how to read this question a little bit. For a standard scale, okay. Your priors for both groups, right? So it didn't say, okay, I tend to get a little annoyed with some of these problems, that they're not explicit enough, my opinion, need to be written. But your priors for both groups should assume a mean of 0 and a correlation of 0 between all pairs. So we have to go back into the course material or textbooks, but in this case, the course material is really what you want to go to. And so for this, everything you need to go to is in the course material, not the textbooks. I think I mentioned early on, textbooks are really good, but some of them expect different levels of background than you might have. And so they're worth looking at and working on and trying to struggle through, or if you get a point, whatever works for you, skim it, take a look at the notation, learn from them what you can. But the lectures in the course and the course material are what you want to look for. So we're assuming multivariate normal distributions, and we want to get a posterior probability distribution for those means, right? And maybe I should go like just draw a picture of what I mean. So no, I'm going to change background. I don't know if I like this. This is too dark or not. Go with the dots and the gray. I don't know. You have to tell me if you have a big preference between one of these or the other. But here we are in 9 dimensions. Okay, now that as soon as I switch to the gray and I start writing, my marker doesn't pop out as well. So maybe I'm being too picky, but right. So I can only draw 2 dimensions. I have 2-dimensional screen, but pretend that's 9 dimensions. And then we have one class. I'll draw it in purple. And maybe I need to use light. Go light blue. Here's my observations. And then there's my mean for this one class. Now, we saw the observations tend to overlap a little bit. So that's maybe coronary heart disease positive. And let me get a coronary heart disease negative class. And we'll sketch what that class. Here's some observations from that class. And its mean is maybe right there. Right, the classes might look something like that. And so what we're doing is we're making an assumption that that each of these can be modeled with a multivariate normal distribution, which I usually picture as a series of ellipses centered on the means. And so the question might be, how certain are we that these means are separate, right? We want to understand, quantify the uncertainty for these means. So we want to build these 2 separate probability distributions for those means, right? The mean is, most likely where we measured it, but it might be anywhere reasonably within one standard deviation or two standard deviations in that within that multivariate probability distribution. These lines, we could think of them as like 1 sigma and 2 sigma. It's not a standard deviation. It's got a different name. It's a chi-square distribution, but you can think of those ellipses as like 68% of the data is within that first ellipse, and the second ellipse encapsulated 96 or 94% of the data or something. Okay, so, but we want to get those two covariances, means and covariances for those two different distributions, and but we want to incorporate priors. So if we didn't use priors, the means for those two distributions would be this mean we computed here, and that mean that we computed there. And then the covariance would be that, the covariance positive, and the same thing for the covariance negative. So those would be your two covariances. So if we wanted to say how separate are those, and we're going to not do Bayesian analysis, we just want to do based on the data, but not consider the priors, then we would do that. But our prior is going to be, let's go see what our prior is, and then we'll go into the text from the class to figure out how to answer this. The prior is assume a mean of 0 for all the variables and a correlation of 0 between pairs of variables. And then we'll talk about this in this. You should assume all variances for the variables are equal to 1. So we'll talk about how those play out in the formulas, and same with this prior on the alpha. And then this here is really the thing, like where it's asking you to give an answer. Okay, so we need to build these two probability distributions, and what we've done so far is build the two distributions based on just the data, but we haven't considered any priors, right? So these are the probability distributions, or the PDFs, for the means based on just what we get from the data, right? It's a probability distribution on the parameters. The parameters are the means for the classes, based on the data, but we haven't incorporated a prior yet. And the mean and covariance for each of these, just to connect it with what we computed, this is the mean for the coronary heart disease positive class. This is the mean for the coronary heart disease negative class, covariance for the positive class, covariance for the negative class. And here we just, printed the covariance here. And I'm looking at, well, we'll parse that in more detail. Okay, so this is computing the covariance, and then it's computing the inverse. So this is going to be playing a role. Okay, now let's step over to the class materials to learn how do we get a formula for the posterior distribution, and this is a multivariate normal probability density function, a multivariate normal likelihood. We have a multivariate normal likelihood, which isn't, I don't know that it's really intrinsic in our data. Usually you say, oh, use the likelihood that is required to model your data. Like we're flipping a coin, it has to be a binomial distribution. So we pick a beta for our prior to go with that binomial. The binomial is just forced by the fact that we're doing a flipping a coin that's heads or tails. Here we made that assumption that it's a multivariate normal, but it's not really forced. It's more like we picked it to describe the situation. So if we go into the course materials and we look at module 2, which is module 2 is called prior distributions, priors. Okay, so we're learning how to deal with priors. And we're learning, in this case, it's going to be multivariate conjugate priors is what we care about. And maybe the problem, here's another thing I would add to the problem, is it should tell you to be using a conjugate prior. But okay, so we go to the video for multivariate conjugate priors. We're clearly in the multivariate class, right? We've got eight dimensions, 8 variables. So worth watching these notes and thinking about this problem, or watching the lecture and thinking about this problem. This little button will give you a download of the notes as a PDF. And so here we have that download as a PDF. So let's see what we have involving multivariate normal distributions. So the first distribution is a Dirichlet or Dirichlet. And I think without going too far down that road, yeah, let's just ignore. You could take a look at this, and if you're curious, do a Google search for the Dirichlet or Dirichlet. Spell it right, pronounce it however you want, and you'll find the right thing in Google, and you'll learn some more about that. But that's not what we're working with. So okay, so now we're into the multivariate normal, multivariate Gaussian with unknown mean and known variance covariance. And so with a multivariate case, often you have too many parameters to do a probability distribution on all your parameters. So usually you say, okay, I'm going to pretend I know some of these, and I want a distribution for the other ones, right? And that's part of the marginal distribution part. So I say we don't unknown mean, known covariance, variance covariance matrix. That's the same thing I call a covariance matrix. NumPy calls it a covariance matrix. NumPy is np.cov for covariance when you're going to use the code. So let's take a look at this. And okay, so let's look at here. So mean vector M with k dimensions. Okay, so that's the vector we already have. A precision matrix tau with k by k, a likelihood with n trials. And so tau is the inverse of the covariance matrix, right? So that's the precision matrix is the inverse of the covariance, right? And so this here is saying we're assuming the likelihood function for our data given m and tau is, and this is proportional to exponential of this, but that's the same thing as saying that this likelihood function is a normal distribution, right? This is the exponent in a multivariate normal distribution. So, okay, so this is the setup saying we're assuming our data is created by a normal distribution. In this case, m is going to be the mean vector for that normal distribution. Tau is the inverse of the covariance. Let's connect that to our computation. So coming back in here, we have two different normal distributions. This would be the mean for the first and mean for the second. So this here corresponds in this to m. And then these are our covariance matrices. Everything there is written in terms of the inverse of the covariance, which we compute down here. So maybe I should call this tau. It's the inverse of the covariance matrix. So this is just an alternate way of computing the covariance matrix. You could get the x positive data and use NumPy to compute the covariance of it. Or you could use this dot covariance that's built into NumPy that you can take a data frame with numerical values and compute the covariance and then convert it to NumPy. So really just two different ways to compute the covariance matrix. So this should be tau positive, and let's do a tau negative. Tau negative. X negative. Oh, we gotta. Okay, so that computes those and just to display something after it runs. Here we're displaying the X positive data, and then here after we run this, we compute the tau, which is a precision matrix or the inverse of the covariance matrix for those two different classes. And then we'll just display tau for the positive class. So okay, so this is good. This should be, if you kind of felt a little like, why are we doing all these pieces? This is starting to bring it together to how do we answer the problem, right? We see that we have the mean and the tau for each of these two different classes, right? That mean and tau, in terms of this picture, give us for each class the mean, which is the dot, the center of the class, and the tau gives you the spread, which we represent with these ellipses. Okay. Now we look at our prior. So what kind of priors do we use in this situation? So the priors, there has to be a mu 0 and a tau 0. Okay, so those we're going to figure out by, it tells us what priors to use. So we have to translate this statement into figuring out, let's call this one red, because that's going to be our final output in red. So we have to translate this statement into what should we pick for the priors over here. All right, so let's look at what these priors are. Priors are mu and a tau, and those two variables are the parameters on our prior. And f of mu Okay, well, I'll tell you what I see on this slide. I haven't watched the video in a while, and sometimes these notations get a little bit to sort through. This tau naught is the inverse of the covariance matrix, or it's a precision matrix for your prior. This is the mu naught for your prior. So this is the prior probability distribution on the parameter mu, right? And so instead of specifying the prior with a capital P, saying here's the probability distribution, we specify that probability distribution by describing its PDF. And so that's what this F is. This is the PDF for mu. And that PDF it's this 1/2 EXP. This is like setting up a normal distribution. I'm not sure if built into here is that's actually a normal distribution, or it's just like proportional to a normal distribution. I'm also, when I see a normal distribution, I see in the exponent normal distribution, I'm expecting a -1/2 up here, and I don't see that. So maybe there's something to think about. It's not going to really impact us for answering the problem. We're just going to take the formulas as they are here. But maybe we'll go explore and see if we can figure that out. But this is a probability distribution on mu, but I don't see mu over here on this side, and maybe I'm missing something. I'm kind of thinking this m is our mu. So let's not overthink this too much, but we have a prior probability distribution on the mean, and mu is that prior's mean, and tau is the inverse of the covariance for that prior. Now, I think I sometimes get lost in notation. Sometimes it's because I just don't think in terms of letters great. Sometimes it's because the notation isn't great. But let's talk about what those priors mean in terms of a picture, because to me, pictures just make more sense. So let's come back to our problem. It says your priors for both groups should assume a mean of 0. So when I say a mean of 0, instantly in terms of the formulas, I'm thinking this variable here is just going to be a vector of zeros. It's going to be 8 zeros. And a correlation of 0 between all pairs of vectors, and you should assume all variants are equal to 1. So, okay, let's screenshot this, because this is pretty easy to work with. And let's bring this over to our whiteboard. Okay. So let's talk about how we incorporate the priors into this and what we're doing. So the prior is like a probability distribution on our parameters before we do any analysis, right? And so so you just have to remember that our probability distribution, our posterior probability distribution, is going to be a multivariate normal distribution, and it's going to be a distribution for the means. So this is our prior. So our prior is going to be, you pick a nice color for the prior that's contrasting these. I guess I can do red because my classes are blue and green. Blue is coronary heart positive. Green is coronary heart disease negative. So I'm going to write my prior in red. So the prior has a mean of 0 for all variables. So my prior is going to be a probability distribution with a mean of 0 for all variables, and a correlation of 0 between all pairs of variables, and assume the variances for the variables are 1. So this piece, let's write it out in notation. Mu naught equals 0, 0, right? The mean for every variable is equal to 0, or the mean vector is a vector of zeros. And that's represented by putting a little dot there. That's my prior. So the red is going to be the distribution for my prior. Then saying that they have a correlation of 0 and the variances are equal to 1, that's telling me that the covariance matrix is going to have variances 1 down the diagonal and zeros for all the off-diagonal terms. In a picture, when we draw the ellipses for that, we draw circles. That means I don't know, I kind of like this Microsoft. This is a Microsoft whiteboard that I'm using. But so these are circles, and it's kind of fun. I can clean stuff up because I'm overly nitpicky. And those ellipses or circles should always be centered on the mean. So in this case, the blue represents our distribution from the data on our coronary heart disease positive data. The green represents the distribution of the data on our coronary heart disease negative data. The red represents our priors. We use the same prior for each of those. And this is a really standard prior. We generally assume, or we often assume, that there's no relationship between things, or that this is similar to when we did linear regression in class. We did a Bayesian linear regression. Our priors were that each coefficient is equal to 0, where the mean prior is a probability distribution. So the probability distribution has a mean of 0 and some standard deviation on that. And the standard deviation describes how certain we are that it is 0, or how flexible we allow it. And we saw that that turns out to be correspond to lambda in ridge regression. And we find lambda, we say by cross-validation, by testing and optimizing, finding the best value for lambda. So we think of something very similar here. This is very similar to ridge regression, but we're doing the multivariate normal case, and our priors is like assuming, hey, I'm going to assume that in the lack of any information, I would expect that there's no relationship between these variables and coronary heart disease. right? And it's kind of like, I'm going to be a little skeptical. Come on, data, prove it to me. You need to give me something useful that is going to be useful enough to prove it to me. Okay, so that's the picture. That kind of explains what we're working on. Let's go back here. And okay, so that explains the yellow we've used. We've talked about that. That gives us a mean of 0 for our prior and a tau that's going to be this. And just to this covariance matrix, we have tau, which is the covariance matrix inverse. And the inverse, of course, of the identity matrix is just the identity matrix. So tau is also the identity matrix. Okay. And then this says the posterior is going to be a probability distribution whose mean is mu star. And here's the formula for mu star. And then this is the probability distribution for the posterior given, given the data, and it's a PDF. F means that we're looking at the PDF here, and it's a PDF on the mean. And again, I think this mu corresponds to the mean, although I'm not quite sure with the notation. We don't need this to describe to answer our problem. This is the piece that we need to answer our problem. Because if we come back to the problem says compute and compare the Bayesian estimates for the posterior means for each group. So here's our estimate for the mean. The mean for each group is going to be tau naught, which is our prior, our tau on the prior, plus n. Now I have to think about n a little bit. We'll come back to n. N is n trials, right? It's a number of observations times tau. And that kind of makes sense. That n has to do with, right? We said as you have more data, your data values become more important, your priors become less important. So we should see that leverage here. And we kind of see that leverage here. So this tau is the tau from the priors. This tau is the tau from the data. And so this is like a weight on the data that increases the importance of the data as we get more data. So it's going to be this inverse times this formula here. Now, this is one of those things where we kind of did the computation of the conjugate of the posterior probability distribution parameters based on the conjugate priors for linear regression. And it took us a long time, right? It was kind of, I jokingly said it's the kind of thing you want to do once in your life, and preferably not in public, right? This computation would be worse, right? So I know there's a bunch of variables here, and if you feel a little bit like, oh, I don't know what every single piece means, that's okay. If we took like 3 weeks, we could go through it and walk through all the computation. The good thing is what you get here is the same thing you would get if you went to Wikipedia. And let's compare these and see what they are. So let's go to this is the conjugate priors pages in Wikipedia. And so here, these are when the likelihood function's a discrete distribution, so that's not our case. And we have continuous, and here's a continuous distribution, but I think this is single variate continuous. So usually, oh, no, the multivariate's in with these. Okay. So we have to go through and figure out what case we're in. Multivariate normal with known covariance. And they do it in terms of covariance or precision, right? Precision is just the inverse of the covariance matrix. And we're assuming we know the covariances and we're doing probability distributions for the mu's, right? So this is really the case we're in. So let's go across and see how this compares to what we have in our data, in our problem. So model parameters, right? So we're just focusing on the mean, right? We're estimating the means of the two classes and we want a probability distribution for those means. The mu naught and sigma naught, right? So our likelihood function is a multivariate normal. Mu naught and sigma naught, those are the prior hyperparameters, right? And so maybe since all our formulas are in terms of the precision matrix, we called it tau. Maybe we'll say we're in this row, right? I'm used to thinking in terms of a covariance matrix, but tau is standard in some areas too. So let's go with that. So these are our hyperparameters, right? Mu naught is 0. This capital, I forget what letter that is. Is it a lambda? I don't know. Oh, well, this is what we were calling tau. It's the precision matrix. And so mu naught's going to be a vector of zeros, and this is going to be an identity matrix. And so when we come over here, this is the posterior hyperparameters. This is the hyperparameters for the posterior distribution on the mean. And what we have here, this should be very familiar. This is the mean for that posterior distribution, and this is the precision matrix for that posterior distribution. So, all right, let's just grab that, take a screenshot of that. And you could think more about the meaning of those things, but we've probably gone longer than we really need to. So this is from the Wikipedia article, and let's compare that to the notes, which are right here. The notes give us this as our posterior. And let's compare those two. Okay, so the posterior, in the notes, it says mu star is given by that. And that's the same thing as this here, right? This is the mean for a posterior distribution. It's a multivariate normal distribution. Tau naught corresponds to that. N times tau corresponds to there's n times the precision matrix. Tau naught, mu naught, that's here. And then n tau x bar, right, is of course that right there. Okay, so this is what we want to solve for. We finally got to the thing that we want to solve for in the question. The question is asking us, what's the posterior probability distribution estimate for the mean, right? In terms of the picture, let's go over that picture. What we are winding up with is we want to combine the data, in this case that's shown as the blue, with the prior, which is shown as the red, and then we're going to get, I don't know the right way to describe it, but maybe something like that, right? As I showed as a blue dot with some highlight around it. And then the posterior probability distribution for the mean in the other case you know, the means will probably be shifted a little bit towards the origin because we're assuming that the means are 0. So let's go ahead and take a look at the formulas and go ahead and do that computation. Really, computation, all we have to do for this computation is go into our formulas and find all these pieces. So see if maybe I can keep that up there while I go into the Kaggle notebook. So there it is. Okay, and so that looks like that's what this piece here is doing. All right, so we want, looks like this is probably what this last little block is doing, but let's go through and compute it piece by piece for this. So mu star positive equals, I need some parentheses. Now I need tau naught. Tau naught, here's tau positive and tau negative. And I didn't give we didn't make variables for the priors. So here's a prior tau. I'm going to call it tau prior just to be clear about what it is. It's called tau naught in the notation. And it's an identity matrix. So that would be NP for Python, for NumPy. And then I think the identity matrix is this. And if I'm wrong, we'll go look it up and then we'll plot it. Nope. Hey, that's good. I guessed right. So there's the, that's what tau naught is. It's the identity matrix of dimension 8, zeros in all the off diagonals, ones down the diagonal. If we looked at like we usually think of those ellipses, this would be an 8-dimensional, well, it would be a 7-dimensional sphere in 8-dimensional space. And just to comment on when I say that about the dimensions, these are 1-dimensional ellipses in 2 dimensions. If everything was up and higher, it would be a 2-dimensional sphere in 3 dimensions. So not real important for that class, for this class or the answer, but just to get my description correct. So we want to build this. That's tau naught. And we probably need a mu naught. So let's, there's our tau prior and our mu prior equals NP dot zeros, length 8, and print mu prior. So there's our taus, and then here's our mu. Okay, so mu star positive is going to be tau prior, just following this formula up here, plus n, and we'll have to figure out what n is. It's just a number. We'll leave it just as n for the moment, times tau, and we're doing the positive case here. Times tau positive. And we're going to take the inverse of this. So I'm going to do NP. Let's go find out how to do an inverse. This here. I always forget the linear algebra, like how to write that. So NP linear algebra inverse. So that's inverse of this. So that's going to get this piece in parentheses inverse. And I just want to check that I'm not covering anything with my writing. And then the second piece, is all in parentheses. So we got to start some parentheses for that second piece. It's in my writing here. There's this parenthesis is a closed parenthesis here. Okay, I know I'm probably being a little too picky, but this really should circle around that. This, I want it to circle around this piece, really just so I can see the parentheses. I know it probably doesn't matter, but I want to see the parentheses go around this whole piece so I don't accidentally lose those parentheses. I'm kind of having fun. So I'm going to put times here for the minute. For the moment, I'm going to put double times. I have to double check what matrix multiplication is in Python. But for the moment, we'll just put that as a holder. So tau prior is this. And then times mu naught. So times mu naught, which is mu prior. Right. So this is going to be a matrix times a vector. So this has to be a matrix multiplication. So let's test how to do that matrix multiplication. I think this is going to fail. Okay, so it didn't fail, but it didn't get me what I expected, right? Precision matrix times vector, this should give me a vector, right? This piece on the left-hand side is going to be a matrix, and multiply that by this vector, we should get a vector out to give us our vector here. So I think this mu prior has to be a column vector, which sometimes is a little tricky to get in Python. So you would think it's a row vector, you take a transpose, that makes it a column vector. So maybe we need to just explicitly say this is this. Okay, so that works. So that takes this matrix, which is the identity matrix, multiplies it by this vector. Now it's going to take this, the vector. It's a problem in Python. A one-dimensional vector isn't a column vector or a row vector. It's just a vector. So it doesn't know, if you do matrix multiplication, it doesn't know how to treat it properly. But this is a matrix times the vector and gives us this. So let's go ahead and put that in for this. And I understand this, taking this class, you probably, there's a lot of these pieces that you were slightly aware of, or you've seen little bits and pieces of at different places. There's a lot of putting things together here, right? You've certainly seen linear algebra, matrix multiplication. You may have seen that in Python, you probably should have, but to take all that together and assimilate it in here is a fair amount of like mental effort. So that's really not a, not a trivial thing. And to understand this sort of vectors and how Python treats them together with the multiplication, together with all these pieces. Anyway, so I'm going to keep this n, it's just a scalar, we'll figure out what it is in a moment, times tau. Now tau is the precision matrix for the positive class, so let's call that tau positive, put that here. And then times x bar, and so that's the mean for the positive class. So let's scroll up and find out where we computed that. Okay, we never computed it, so let's call it mu positive. And maybe it's mu bar in this example, or x bar. It's the data estimation of the mean. So I'm going to call it x bar positive. And if you called it mu, it's the mean of the positive class data. That's okay. But because we have a couple of different mu's running around, I'm going to call this variable x bar positive. X, the bar means we've estimated this as the mean, and it's the mean of our data, right? So for the positive, it's going to be this. Huh. I just did something and I can't undo it. Stink. It broke it up. So weird. Okay. I don't know what I just did. whatever I did, it broke up this block into a bunch of pieces. So I reassemble it. That cell, really, and delete the cell. So X bar positive is this, and then I want to print X bar positive. Here and oops. Oh, let's go. CHD positive. Mean. And so that does the positive case, and let's do the negative case. So the case where C with CHD negative. So X bar negative is this. We're going to take the negative CHD values, and then we're going to print those. So this should give us the same values that we saw before when we computed the means of the two classes. But now we've given them names, X bar positive and X bar negative. So let's come down here. X tau positive. And we want to do tau, just a tau for the class looking at times X bar positive. And again, this should be matrix multiplication. Times that. Okay, and then again, this first piece in parentheses raised to -1, that's in a matrix. We take its inverse and we multiply it by that to get the mu. So what we want to do is do a matrix multiplication on this full thing. See if I can shrink that, maximize this so we can see the full formula here. So it's matrix multiplication. This is that first piece. This is that second piece in parentheses. And I think that should do it. So let's see, this is our mu star positive. Oh, n is not defined. So n, let's go back to, where are we going to compute n? N is the number of observations. So let's go ahead and compute this back here. Observations for CHD positive, and let's call that n subscript positive. And it's not going to be an array. I think we can just do the length of that. So let's do the same things for negative. And put that in, and negative. And I think we saw these numbers before. And negative's not defined. Oops. Okay, 160 and 302. So those were things we saw above. And so now when we go into this computation, this n in this case will be n positive. And n is n positive. Operand's going to broadcast together. It's weird. Okay, what if we just put 160? and 160. What if we drop the n's? I want to see if it's the problem with the n. Okay, so I think this, what's going on, this is giving me what I care about. That's correct. And the second piece, this n, sorry, let me finish this thought. It's n times x bar. That n goes, and n is this times tau times x bar. Okay, so it's telling me this second array is 160 by 160. So it's telling me this whole array is 160 by 160. So from that, I'm guessing there's something fishy, tau prior, in one of these pieces. So let me take a look at that. Okay, so it's really, the problem is in this piece here. The tau prior is 8 by 8. The tau positive is this. Okay. I'm pretty sure I know what's going on. So this tau positive, it's an array of 160 by 160. That's a problem. My covariance matrix should be an array of 8 by 8. And so when I take its inverse, I should get an 8 by 8. So the problem is this is not, this is switching the dimensions, right? The data is tracing this problem back through the code. It's 160 by 8, 160 rows, 8 columns. Okay, that's fine. That's pretty reasonable. We take its covariance and we look at that. Taking the inverse doesn't really do anything to the shape. And so the shape of that's 160 by 160. So really what I need is to transpose these just so that they, or maybe I don't want to transpose them here. I need to transpose these before I compute the covariance. So it's treating we have 160 observation of 8 variables, but when it's doing that covariance computation, it's treating it like it's 8 observations of 160 variables. So put the transpose there. Now our shape is correct. It's 8 by 8. If you notice, when we did the this covariance computation off the data frame with the .cov, let's see what the shape was up here. My guess is that would have handled it right. Yeah, so that would have given us the right thing. That's 8 by 8. So the only really mistake that we got with our dimensions is when we tried to recompute it. So we recomputed it first with the pandas data frame covariance method. That worked just fine. And we recomputed it with the NumPy cove off of the data, but it turns out for this NumPy method, we have to transpose the data so it understands it and gets the right shape. Okay, so this should give us, yeah, so that gave us no problem. So now we can get our answer down here. Okay. So his shape is 8 by 8. So that is this piece. Let's take this piece. So it's complaining about dimensions and multiplications of data. So I expect there's probably something similar here. Okay, so we're trying to add these two pieces together. And all right, let's see if these, so that gives us a vector of length 8. And this gives us, okay, so it's saying I can't multiply that times that, because there's a dimensions mismatch. So tau positive dot shape. Let's get the dimensions of, right? That's our 8x8 identity matrix for the prior on the positive data. And let's get, these are just kind of my scrapwork boxes. The X positive shape, it's 1/8. So it's saying I can't multiply that times that, right? So maybe I need to transpose this. And now I've got a correct answer. Okay, so I'm not sure if I'm going to need to transpose things again or anywhere, but transposing the X bar positive gave me, right, this is 1 row by 8 columns. So that's a row vector. And here I'm trying to multiply without the dot transpose. It's a matrix times a row vector, which is going to fail. It needs to be a matrix times a column vector for that matrix multiplication to work. Okay, so let's see if this, it worked. Let's see if we get a reasonable answer. Okay, so I was expecting a vector of length 8. So this is early on in this video. I said, we just need to go through and I need to post this for you. It usually takes me a long time to kind of build a cleaned version, and you're getting the full, like, how do I produce the solution and give the answers? So when it adds these two pieces together on the right-hand side, which, you know, because it's not clear, it's taking me a long time to put the full thing together. Okay, so this is giving me like a matrix on the right-hand side. I want this plus that to be a vector. So this has that shape. This is the second piece we're adding it. It's the tau positive times X bar. It's the tau positive times X bar, and it's multiplied by the N. And it's giving me a column vector. So to add these together, I'm not sure the simplest way to do it, right? Sometimes I just transpose it. Yeah. So I need to transpose this back to make this a row vector. And I'm going to add it to this, which is the row vector for my prior, which is that. Okay, good. Do I care? This has got double brackets. This has got single brackets. That might not matter. Let's just see what Python thinks the shape of each of these is. So shape of that is 8, 0. Shape of this is that is 1, 8. Okay, so there's a couple of ways to deal with this, I think. NumPy has an operation called flatten, or maybe it doesn't. NumPy thought. Oh, it's ndarray.flatten. Okay, so numpy.ndarray.flatten. So it flattens the array. It kind of takes away the the dimensions or any excess dimensions. So let's see if that, so that will make them both the same, and I probably don't need this transpose if I do that. Yeah. Okay, so I'm going to put this piece here. This is my tau prior, mu prior. That's this. Tau prior, mu prior. Then I'm going to put this in for that second piece. And that's this. And let's go ahead and run it. Okay. Let's see. Plus 5. My guess is I have an extra parenthesis in here. And yeah, okay, so this green says that's closing this. And so I need another parenthesis, I think. Yay. Okay, so this is a big deal. This is the answer for the mu star question. And so the mu star positive, that's the mean of the posterior probability distribution for the coronary heart disease positive case. And it's this sequence of values here. And so what I want you to do is compare. So for the homework, save version, save and run all, commit. I'm going to save this. I'm going to share it. I'll make it public. I might, you know, for future versions, for future classes, depending on how they're turning out, I might make this, remove the public part of it. But I know we've, you know, for the status in our class, I think it'll be helpful for you. And what you'll need to do to finish the homework, well, follow this video so you understand all the pieces. And this is the mu star positive, which gives us this. This is your posterior probability distribution estimate for the mean of the positive data. And see if that compares correctly with this picture. That the positive data, the data mean was here. Our prior assumes it's close to 0. So this mu star positive should be, you know, taking the data mean and pushing it a little close to the origin, right? Similar to what we've talked about in the coin case, but right now we're in 8 dimensions instead of 1. Now we're using multivariate normal distributions or multivariate Gaussian instead of binomial, but very similar to what we did in the coin case. And let's see, I'm going to share this notebook in Kaggle. Okay, and it ran, so you'll have a version that's run all the way through. So this is mu star positive. So what you'll need to do, what you should do for the homework is compare that to the mean for the coronary heart disease data. So this is just the data by itself. Right, if you estimated the mean just by the data by itself. This is the estimate of the mean using the data and our prior. And then you'll need to do the same for mu star negative and see how the prior affects mu star negative. And I want you to compare those and give some thought. I mean, it doesn't have, I'm not expecting anything very long for that thought. But compute, we did it for the mu star positive. You'll need to do it for the mu star negative part. And then compare the Bayesian estimates with the means for each group, right? There's a 5 extra points part here. You're free to think about it. I'm not going to walk through it. But I'll just kind of tell you what it's asking about because it's interesting just like seeing it. So yeah, I don't think it's worth. You're free to work on it and think about it. Okay, so problem 6. I'm going to do a second video on problem 6. So that finishes everything from problem 5. I think this notebook together with the video will provide you what you need for problem 5. Okay, take care. Hope that was helpful.